I don't quite understand this question. What is file system?
The homework, it uses abbreviations when asking the question. So he's asking what the FS stands for.
Oh, okay. I'll check that one and get back to you. All right. This is our setup. So, we started by choosing our group ZP and then also the subgroup ZQ. We form the polynomial f of x, and then we compute everybody's share. And then now we are ready to publish our public key. So if we assume that here is the public bulletin, then we would have a sort of a table. We have G, we have P, we have H, which is equal to G to the S. And then we have H1, H2, all the way to Hn. So these are our public parameters. User. Okay. So now that we have set up our system, now user can show up to cast their votes. For example, Alice would come and say that this is my vote C1 and this is my signature. Anil Alice's key of C1 so that nobody can change it. Bob would show up, would cast C2 and sign this C2 under Bob key C2 and so on and so forth. So okay, cool. So far we have set up the system, people are casting their votes, but we need to have some requirement. Every time that somebody does cast their vote, for example, Alice says that this is my vote, so we can't just accept her vote. We need to check if her vote is correct, so we need to check or need to prove that the vote C1 is correct. By correct means that it should be a yes or no, which is +1 or -1. Not something like +10 or something like -10, right? So it is acceptable for somebody to have a vote if they vote for only +1 or -1. But if you see, we never check if Alice can be malicious user and she just say +10, 10 times yes. So she's one person, she can just say one yes, and she cannot vote as 10%, right? 10 people. So this is something that we need to be careful about if we are now designing something that is more robust system. So overall, these are, I'm going to list our requirements over here. So maybe I can change my pen color. So requirements. So number one, we want to make sure that the votes are secret. Okay, so no one can learn the content of the votes, not unlike the first one that the trustee T could basically see the votes. Two, we need to authenticate the vote. that they are coming from the right person. Also, they are valid, they are correct. You know, they can't, nobody can count as 10 yes. Everybody can count, just vote as 1 yes or 1 no. 3, make sure that every vote is counted. And then 4, nothing can be tampered. That means that, you know, when somebody casts things over here on the public bulletin, they can't change it. They cannot, you know, somebody can swap them with something else. So these are our basic requirements. And from now, we are going to see how we can basically design this new crypto system or, you know, voting system that satisfies all these requirements. In case of the voting, so again, we are going to use our commitment scheme. So everyone is going to cast a vote. So the vote is encoded as, you know, we are going to encode this one as G to the power VI. So every time that you want, somebody wants to vote, they would basically generate a random number, alpha I, from ZQ. And then we will compute the vote, which is going to be G to the alpha I, and then G to the VI times H to the alpha I, you know, where H is or G to the S. And therefore, we are going to publish these things on the public bulletin. So suppose that I get the vote for user I and J. So CI, I get G to the alpha I, and then G to the power VI, and then H to the power alpha I. And then for user CJ, I get G to the power alpha J, and then G to the VJ and H to the alpha J, right? So if I compute CI times CJ, what I will get is G to the alpha I, and then G to the power VI plus VJ times H to the power alpha I plus alpha J, right? So even though we slightly change our format, we still have this commitment scheme. We still have this homomorphic property, so that, you know, when the user casts their votes, we are able to, you know, to do our computation correctly. So not much of change as the way that we were voting. So this is gonna be a tally. So so this is how, you know, after we do the voting, this is the way that we are going to see how we can count the votes. So without lose of generality, we are going to assume something, that we have a set, index set of J, the capital J, that is a set of those trusted or honest authorities. So we said we have N authorities, but let's say T of them are honest. So for that, we are going to say that, let's say A2 is honest, A4 is honest, I don't know, A6 is honest, all the way to some AN minus 3, for example, where the size of this J, the size of this index set J is going to be T, right? So we have T honest authorities that they come together And this is the computation that we assume we are going to do based on the information that they provide. And then we are going to see if we can show that we can recover the votes or not. So once we have got our computation, these are what we are going to do. Number 1 and number 2. For number 1, we are going to compute or C tilde, which is multiplication of every part, and at the end we would get something that we call it C1 tilde and C2 tilde, and so this is how we would denote them. So after we do all the multiplications, so suppose that this is my C1, C2, equals to, let's say, C1, 1 and C1, 2. And then this is equal to C2, 1, C2, 2, all the way to Cn, which is going to be Cn and 1, Cn and 2. So when we multiply them together, so we are going to basically multiply all of these guys together. So at the end, what we would get is we're gonna call this one C1 tilde, and the second part, after we multiply everything together, we're gonna call that one C2 tilde, right? So together, after we do this computation, we get C tilde, which is the multiplication of all of them. It's going to be C1 tilde and C2 tilde. Okay, this is the notation that we are going to use. So looking into this closely, what we get is C1 tilde is going to be g to the power alpha 1 plus alpha 2 all the way to alpha n, which is, we can denote it as g to the summation of alpha i's. C2 tilde is going to be g to the power v1 plus v2 all the way to vn times h to the power alpha 1 plus alpha 2 all the way to alpha n, which we can denote this one as g to the power sigma of vi's plus times h times sigma of alpha i's, right? So this is so far what we have computed for number 1. And then, okay, we are done with that. So for number 2, we are going to compute every tally now. If this is like what every honest authority would do this computation. So 1, they would multiply all the votes to each other and will compute C tilde. Then once they have computed that, they are going to compute some other value and publish this one. That they're gonna take this C1 tilde, the first piece, they raise it to the piece of secret key that they have, piece of share from the secret S, and then they're gonna publish it as WJ. So if I go back and I do this computation according to our index at J, so A2 would publish W2 equals to C1 tilde maybe I can write it a bit lower. So W2 time equals to C1 tilde to the power S2. So this is what A2 would publish. A4 would publish W4 equals to C1 tilde to the power S4, and so on and so forth. Right, so n minus 3 would publish Wn minus 3 because C1 tilde S n minus 3. Okay, of course everybody else would also publish, but we said that we suppose that these are the set of our honest users, so we are only looking into their computation. So this is like number 1 and number 2 done. So now that we get this one, then every user can compute the actual sum of the votes by performing this computation. So by getting the C2 divided by multiplying these WIs that every authority has output to the power their lambda j, and then we are able to reconstruct this vote. So let me go down. Let me also change with the color so we know we are talking about different thing. So the point is, if we are given, let me write it this way. If you are given the secret S, if we knew the secret S, then we could basically recover the votes. How so? If we knew the secret S, then we could just do C2 tilde over here divided by C1 tilde to the power S, and let's see what do we get. We get C2 is G sigma of VI times H sigma of alpha i's, and then we would get C1, which is or S, right? So it's interesting to see that this part would become G to the S. You can rewrite it as G to the S sigma of alpha I, which G to the S was our H, right? So if I go back, we define, when we get the secret, we let H to become G to the S. So if that is the case, then G to the S becomes H to the sigma of alpha I. Then that means that this 2 can get cancelled, and then the result would become just G to the power sigma of VI's, right? So how so how to compute V, which is V2 plus all the way to Vn. So we know that V could be somewhere from minus M to M. If everybody says no, we would get minus M. If everybody says yes, we would get plus M. So then we can compute V by doing this computation, G to the power minus M, G to the power minus M plus 1, all the way to, we start from there, and then we continue to some G to the power V, and then this one output V, right? So we write a for loop, and then we compute from minus M all the way to the place that the result would equal to G to the V. And if that is the case, then we would just halt. And then we said that, the result is just the index of that for loop, which is our V. So then, this is like, this becomes very easy to understand that, okay, if we were to have the S, the secret S, then we can recover that. So the point is, now we don't have the secret S, but what we have is that if you see over here, these users, they have provided their secret S, the piece of S. So we are computing the rate of your computing over here is this thing. We are computing the pi of wj to the lambda I. If I raise it to the power lambda j, then I'll get c, for example, c1 tilde of sj lambda j, which we said that, you know, it is equivalent of, if we go back to our formulas, this is like f of j and then lambda of j, right? So if we do this multiplication and then we compute the f of that 0, then we are basically we are doing the computation for our retrieving the secret S. Let me put it that way. So the only question is that how do we compute this lambda j's? So we know that we use the fixed i's for computing that j. So let me go back. So for over here, you see that we compute the 1 for every 1 is like f of 1, 1 of f of 1, 2 of f of 2, which S2 is f of 2, equivalent of f of 2. So this indexes i's that we need over here, the x points that we need to compute the lambda are already known. So because we are having an index set, so then we have problem with this one, but actually it's authorities. So authority 2, 4, 6, and n-3, those indexes are enough for us to compute this lambda j. And when we compute that, then, you know, we are able to recover the S. So so now when given the secret S, we could recover this one. But now how to find the S? So the S was like, we said that A2, A4, and so on and so forth to AN-3 get together. We got their shares. And using this, so we said that we can combine them. We can recover the S, right? So using that schema that we've discussed in the previous page, that we call it Shamir secret sharing, we are able to actually recover the S, given, you know, the pieces of every authority, given share of every authority, share of the secret key, we are able to recover that key, and therefore we have no problem to reconstruct S if there are T users there, T authorities there, and therefore we are able to count the votes. All right, so this looks like that we are going to the right direction. So, but there are some few things that we need to clear out over here before we really go forward. And these two are very important. Number one is that we want to make sure that everybody has voted in a correct way. That means that when the user VI voted as a yes or no, and they are indeed in the format of yes or no, right? So that you know, that is case number one. That is that saying that for case number one, we are looking into the VI's vote, and it has to be one of these four. G to G alpha I, or G to the alpha I and G minus 1 H of alpha I, right? So it has to be one of this format, right? So this is the first thing that we need to discuss. So that is the case number one, and two. So we said that in part of the computation, every authority would output some WJ, which was the S1 tilde to the power SJ is private key. So we need to show that he's using the correct SJ. Otherwise, we are not able to, recover the actual vote, the sum. So we need to somehow push the prover to give us some proof that what he provided us is basically correct. So for number 2, what I'm looking for is that we know that we have this authority AJ, that he has this h of j, which is equal to g to the sj. This is a share. So this is from public information that I have. Also, in the middle of computation, this same guy has to provide me the wj, which is equals to c1 tilde to the power sj, right? So this thing is in the public parameter. So if you look here closely, it looks like that he is using the same piece of information in 2 locations, one in the public key, and then he has to use that one again throughout the computation to prove that, to finish his computation and allow the users to recover the S and therefore count the votes. So what we are seeing here is that we have 2 values, J or G or C1 tilde, and then we raise them to the same power. So what we are trying to do here is to show that, to prove, AJ has to prove that he used the very same SJ and he raised this C1 tilde to the power SJ as a proof of his correct work. So we need to be able to verify that. Otherwise, we wouldn't be able to count the votes correctly. So what we are trying to do is that we want to prove of equality of the logs. So that means that if you imagine, if I get the log of hj to the base g, this is going to be equal to wj to the base c1 tilde, and this both sides are going to be sj, right? So I want to prove that 2 log has the same exponents, but with this have the same exponent but with different bases. So 2 logs, this is what it's saying, 2 logs with the same exponents but with different bases. Okay. So this is the case. Okay, now you can hear me. Okay, awesome. Where was I got caught up? I feel like I had a network issue here. What was the last thing that you heard? Okay, so I'll go a bit back in case. So we said that every authority have to provide us this WJ so that we can recover the votes, the counts. But we need to also make sure that if he's an honest one, he has to raise this C1 tilde as a computation to the SJ to his share. Then we noticed that he used the same value for his public key, which is HJ, which is G to the S. So one way for us to prove that for authority J that he did the correct work, proof of work, that he indeed used SJ for computing this WJ, is to show this 2 equality between the logs, that we basically want to show that we have two logs that, the exponents are the same as j, but with different bases, so g and c1. So that is what we are trying to say, that this guy can solve this problem, can compute this, this grid log for two bases under the, for two exponent under the same different bases. So we were trying to change those variables to make it more understandable. So I denote g1 as g, y1 as hj. I'm going to say g2 equals to c1 tilde, and y2 is going to be wj. And then my x, I'm going to let it to be sj, right? So now we are trying to say that the problem we are trying to solve is that log of y1 on basis of g1 is equal to log of y2 on base on g2, which is going to equal to x, right? So if we can prove, if now the every authority after publishing this wj, he also need to provide us a small proof that indeed he uses the same exponent. So he has to solve this problem for us and prove to us that he indeed used the same exponent. All right. So that is roughly what we want to do. So if you look into the voters, so we show that the voters' vote is basically some sort of they have to prove that they vote for for two values. So we said that the VI's vote he can vote either for g to the alpha I and then g to the h alpha I, or he votes for g to the alpha I and g minus 1 to h alpha I. So he needs to prove that his vote is one of these two cases, but not everything else. So in order to prove, he has to show that either CI equals to C1 and CI and 1, and then C I and 2 times g to the minus 1, which is going to equals to g to the alpha I and then hi alpha I, or CI equals to C1 CI1 and then CI and 2 times G, which is going to be g to the alpha I h to the alpha I, right? So if you look into the votes, they are different because it could be g to the hi, or the second part, or g to the minus 1 to the hi. But so now he wants to prove that he has voted correctly. In order to prove, well, he doesn't also want to, this voter doesn't want to leak what was his vote was. So therefore, we need to also find a proof. And then he only need to prove one of them because he's voting for one. So if you notice that if for the first one, we multiply the second part to the g minus 1, so we get this value. And for the second one, if you multiply g, then we would basically cancel this effect and we get this one. So it looked like that there is a trick that we can use over here. And then to prove that we have this user vote is correct, but the results are indistinguishable to the eye of everybody else. And that would be a very good way to prove them. But the challenging part is that this voter has to prove for one of these two cases, not both of them, because he's not voting for both yes and no. But the thing is, like, nobody should know which one he is proving his vote to be, right? So that's why this equal result at the end could work, could help at the end. So we would get back to this very soon. So again, the idea is to use the proof of the equality of logs on different bases. But let's get into this one and see how this proof of equal logs would work and why is it actually helping us to prove that we can use this scheme for proving somebody's work is correct. So we want to prove this one that y1, which is g to the x, is actually equal to g1 to the x is equal to y2, which is equals to j2 to the x, are equal. So they have the same discrete log. They were raised on the same exponent. So the idea is that, so again, we have a prover somehow that we want to prove under some to some verifier, which is the prover is the authority, verifier as those people that they are voting. So the idea is to randomly get the R from ZQ, and we are going to use the same identification scheme with some variation. So we compute A1 because G1 to R, and A2, which is G2 to the R, and then the verifier would send us some challenge C from R on ZQ, and then we are going to return a B value, which is R minus CX mod P, mod Q, and then once we are done with this, we can check the correctness. So we said A1 we should check if A of A1 equals to G1B that Y1C. And also we should check if A2 equals to G2B and Y2C. So in order to check, let's plug this in. So G1 to the power R minus CX times Y1 was G1 to the X, so XC. So then you see that this one is going to be G1 to the R. That is correct. So A1 was G1 to the R. And similarly over here, we get the same result. So we get G2, which is R minus CX times G2 XC, so we get G2 to the R. So it looked like that. We can use this identification scheme that we've talked about in the last lecture, and we can use this one to prove that somebody knows some secret, that based upon that secret he can compute two computation based on different bases. And we just slightly modify it so that we send two challenges under two different bases that we have. We receive this one challenge, and then we also respond with one value, but we are able to recover to show the proof that we are correctly doing the computation. So let's see what are the chances if somebody doesn't know the prover can cheat, right? The prover here being authority J that doesn't know the SJ, his share of secret key, and being able to cheat by using this protocol and convince the verifier that I used the same SJ, but he didn't. So in order to understand that, we say that the adversary or dishonest prover can cheat with a probability of 1 over Q. So that is the only chance that is very low. The soundness is the completeness we discussed. The soundness, if the P star can cheat with probability of 1 or more than 1 over Q, then it can find, it is not possible to cheat for 2. So if we imagine the computational tree for this prover, so he can go through many different routes of different values that he could choose for A1 and A2. So suppose we are here in A1 and A2 on the, this guy doesn't know secret X. So then that means that if he can cheat with probability more than Q, it means that he can answer for more than one challenges. So C and C prime. I think you already know how we can cheat. You can just basically assume what the challenge would be and prepare for pre-compute A1 and B2 so that he can successfully pass. But when we are saying that he can cheat with more probability more than 1 over Q, then it means that he can guess two different C's. And therefore, for that, he can compute two different B's, Cx, and this one is going to be B prime equals to R minus Cx. And then if that is the case, then we know that we can utilize this one to compute X, right? Like if somebody like this sort of prover claimed that he can solve it for some branch, he can answer for two challenges, then we know that we can use that one to, to compute or X, which is our secret key. So we can solve discrete logarithm problem basically. So if we deduct both sides, we get C minus Cx plus C prime X. So then X equals to B minus B prime and then C prime minus C, right? So it is not possible for somebody to cheat with probability more than 1 over Q. So this scheme is also not is not a zero knowledge proof for any verifier. In order to understand that, is that we need to design the simulator. So just for your reference, this simulator S that on given G, Y1, G2, Y2, and the verifier, then the first thing he has to do is randomly select B and C from ZQ to compute A1, which is G1 to the B, and Y1 to the C, and A2 equals to G2 B and Y2 to the C, and 3 if he calls the verifier by this input Y1, G2, Y2, and A1 and A2, and then if this thing equals to the same challenge that he guessed in over here, then he would return A1, A2, B, and C as the accepting transcript. But we know that there is a problem here that this simulator is not polynomial time. So we know that over here, this probability is only 1 over Q, right? Because there is Q different choices for C, and Q is quite large prime. So this probability is very low, and therefore the expected runtime of S star is going to be Q times, some polynomial time. Polytime refers to this part. So we know that number 1 and line 1 and 2, these are polynomial time computation, but when you multiply the exponential number, they are not polynomial. So this thing is not a polytime algorithm, right? So and therefore we are not able to show that this is a zero knowledge proof. So let me recap quickly. So what we wanted to do was that we go back to here So we show that, at some point of the computation, every authority AJ has to provide us this WJ, because these W's are important for us to recover the S, and therefore we can count the votes. But they need to compute the C1 TIL and raise it to this piece of share that they have. So, well, we said that they're honest, but we need to verify their work. And in order to verify their work, the only way we had was that to show that this SJ is exactly the same value that they use it for computation of HJ, which is a part of the public parameter. So we show that it looked like that they are computing, this two different values, two different bases. They raise it to the same exponent. So the idea was that, so it looked like that we are computing logs, discrete logs under two different bases for the same exponent. And we just, over here, we just change the variable name to become a bit more generic. And if we can show that the same exponent is being used as a log of two different values, then it means that this authority J is basically using the same correct value, the one that he used for HJ, he's using the same SJ to do this WJ computation. And this proof would be enough for us to say that, okay, I'm going to trust this WJ from this authority AJ, and I'm going to put this one as my trusted authority because he did the computation correctly. That's one of the ways that we can distinguish who is honest authority and who is dishonest. So, ideally, the dishonest prover, dishonest authority shouldn't be able to prove this thing for us with probability more than 1 over Q. And we show that if this is more than 1 over Q, this means that this authority is basically, we can use this authority to solve the discrete logarithm problem. So this is not possible for him to, cheat with probability more than 1 over Q. So yeah, so we are all the way up to here so far. And it is very interesting that, not only we can get the computation from every authority, but we can even have them to prove it for us. And so this is very interesting, so that we won't have to trust them by default. We can verify their computation and say that, okay, you look like that you use the same, the correct SJ or piece of share for this computation. All right. I think we would, continue with some discussion about the honest verifier over here, but I think it is your break time. So let's just take 10 minutes break time, and then we will come back to continue on this.